Okay, so this is based on joint work with Cédric Boutillier from Sorbonne Université and David Cimasoni, who is in Geneva. Okay, so here's an outline of the talk. So first I will tell you about the dimer model, and then I will tell you about the dimer model and how it is related to Harnack curves. And this will lead us to speaking about minimal immersions and the elliptic dimer model that we're considering. And then finally, I will speak about results that we obtained. So please do not hesitate to stop me. If something is not clear, you can just interrupt. I cannot look at the chat at the same time, so don't just interrupt me if you feel like it. Okay, so the dimer model comes from statistical mechanics, and it represents the absorption of diatomic molecules on the surface of a crystal. So it's modeled as follows. You consider a planar bipartite graph G. So bipartite means that the vertices are naturally split into two colors. Here's black and white. And a dimer configuration is a subset of edges such that every vertex is incident to exactly one edge of this configuration. So these edges represent the diatomic molecules. And then you introduce a parameter on the model, which is a positive weight function on the edges. And this allows you to define actually the model. So every dimer configuration occurs with a certain probability, which is proportional to the product over all edges in the dimer configuration of the weight of the edges. And so you have a normalizing constant so as to make it a probability measure, which is called the dimer partition function. Can you see my mouse if I show with my mouse on the screen or not?
Yes.
Yes? Okay, so then I can show where I'm at. Good. Okay, and so one of the key tools to study the dimer model is what is known as the KASTELEYN matrix. Okay, so if you want to compute things, so typically what you want to compute is the partition function, the Boltzmann measure. You want to try and find explicit expressions. So often in statistical mechanics, you cannot get explicit expressions, I mean closed formulas, but for the dimer model you can. And what is the tool to do this is the KASTELEYN matrix. So I will define it. The definition is a little bit technical, but what you should think of is that it's an adjacency matrix of your graph. So it encodes the adjacency of your graph. So before going to the angles, to tell you if you don't know what an adjacency matrix is, you will have lines indexed by, rows indexed by white vertices, columns indexed by black ones, and you have non-zero coefficients if and only if the two correspondent, if there is an edge corresponding to the vertex W and B. Okay, so this is why it's called an adjacency matrix. It codes the structure of the graph if you want to. Okay, so how precisely is it defined? So to every edge WB, you assign an angle phi WB, which satisfies a technical condition. Okay, you have to have that around a face, you have to satisfy some parity on these angles. Okay, it should be equivalent to k minus 1 times pi mod 2 pi. And so once you have these angles, they define phases for your KASTELEYN matrix. Okay, so on each edge you have a phase defined as exponential I phi. And you also put what is important, the weight of your edge, nu WB. Remember, every edge had a weight, so you put the weight of the edge. So it's a twisted, because of this angles, weighted adjacency matrix. Okay, and so this is the key tool to studying all the model, and it was introduced by KASTELEYN in the 60s. Okay, and so the main result, so I told you it's what you need to compute things in the dimer model. So how do these results work? So suppose that the graph is finite, then KASTELEYN in 61 proved that the partition function of your dimer model is equal to the determinant of this KASTELEYN matrix in modulo. Okay, and I also cited Cooperberg because he introduced the KASTELEYN matrix with the phases. So I'm going back here. In the version of KASTELEYN, you had signs. You had plus or minus signs put in a clever way, okay? And so why is this result true is that if you write the determinant as an expansion over permutations, you see that the terms, the non-zero terms, exactly correspond to dimer configurations, which are also perfect matchings. And then you have signs in front coming from the signature of the permutation. And this is where the phases come in, or the signs if you use Castellane matrix. You have to ensure that all the terms in your determinant come with the same sign. Okay, so this is in 2 words why you have such a formula. And then once you know this, using basic probability, you can compute the Dimer-Boltzmann measure explicitly. So if you consider a subset of edges E1, En, then the probability of all dimer configurations contained in this fixed subset of edges is explicitly given by the product of the Castellane matrix on these edges times the determinant of the inverse matrix restricted to the vertices of these considered in your subset. Okay, so the bottom line of this is that knowing the determinant of the matrix and the inverse of the matrix, you can compute all basic quantities of your model. So this is when the graph is finite. And when the graph is infinite, then the notion of Boltzmann measure is naturally replaced by that of Gibbs measure. And you also wonder, can you obtain explicit expression for Gibbs measures in the infinite volume case? And so there are results, quite a few in this direction. So when your infinite graph is periodic, then you have explicit expression due to Kohn, Kenyon, and Prop. So they handle the case of Z2, so the specific case of Z2. And this has been generalized to all bipartite graphs by Kenyon, Opunkoff, and Sheffield in 2006 in a paper in Annals of Math. Then you can also wonder, can you do things when your graph is non-periodic? Okay, and so this uses different techniques, and we had some results in this direction. I did things in my thesis, then we worked with Cédric Boutillier and also with Kylian Rachel in some specific non-periodic cases.
Excuse me, naive question. When G is infinite, do you observe anything like a phase transition, some new phenomena that you wouldn't?
Sure. Yes. So exactly. So that's a very good question. So you can ask yourself. So you have a notion of Gibbs measure, and so as usual in the statistical mechanics, you wonder, is it unique, or do you have a phase diagram with different regimes? Okay, and so actually so I will tell a bit more about this, but for the dimer model, you have when the graph is periodic and bipartite, you have a 2-parameter family of Gibbs measure with a phase diagram which is completely known. So I will tell more about this. Okay, so that's also one of the feature of this model, is that really you can do everything explicitly and you have a completely explicit phase diagram. Does that answer your question?
Thank you, yes.
Okay. So now, yeah, we will look more in detail at the periodic case. Okay, so we assume that our graph is bipartite, infinite, and Z2 periodic. Means that you have a lattice Z2 acting invariantly on your lattice, on your graph. The period here is quite small, but you can imagine it can be as big as you wish, but it has to be finite. Okay. And so to study the graph on the infinite lattice, what you do is you take an exhaustion of your infinite graph by toroidal graphs. So they will be referred to as Gn. It's G quotiented by n times Z2. So here, for example, putting it on the torus just means that you identify opposite sides. You take n times n copy of your fundamental domain of your little structure and you glue it on the torus. Okay, so this is what we'll be considering. So in the case of periodic lattices, actually, as we will see, all the information is encoded in the fundamental domain, which is the smallest structure of your lattice. It's G1, okay? It's G quotiented by Z2. So how does this work? So this is taken from the paper from Cohn, Kenyon, and Propp, and then Kenyon, Okunkov, and Sheffield. So you take your KASTELEYN matrix, as I defined it before for finite graphs, of your fundamental domain. So you take your KASTELEYN matrix for this little graph, and then you multiply edges that cross. You see, as you're on the torus, you have two non-trivial cycles that go around the torus in the two possible non-trivial directions. And then what you do is you multiply the edges that cross these non-trivial cycle, one of them by W or W minus 1, and the other by Z or Z minus 1. And the choice between W or W minus 1 depends on whether you have a black vertex on your left, say your cycle is oriented in this direction, or a white vertex on the left, and similarly for Z. So this now gives you a matrix which also depends on Z and W. Okay, so it's the let me repeat, it's the same KASTELEYN matrix as I defined before with the weight function and the phases, and it has an additional weight Z and W. And so you have this matrix depending on two complex parameters, and from that you define the characteristic polynomial, which is the determinant of this matrix. Okay, so it will be a Laurent polynomial in the variables Z and W. So for example, if your weight function is identically 1 on all edges, and you do the computation of the KASTELEYN matrix, which will be a 4 by 4 matrix, you put the weight Z, Z minus 1, W, W minus 1. For the example that I'm showing, the characteristic polynomial would be 5 minus Z minus 1 over Z minus W minus 1 over W. Okay, and so if you want to know about the phase diagram exactly of your model, what you need is to introduce these two objects. So the first is the spectral curve. So the spectral curve is the zero locus of the characteristic polynomial. Okay, so as there's been quite a lot of algebra, it's maybe clear to you, but so it's referred as a curve, but you should think of it as a two-dimensional surface living in a four-dimensional space. Okay, so you should think of this as a surface. And since it lives in a four-dimensional space and that it's quite difficult to see, what they usually do in algebraic geometry is to consider the amoeba of the curve. So the amoeba is the image of the curve through the mapping ZW goes to log modulus of Z, log modulus of W. So here on the picture, I have pictured the amoeba of the curve of this characteristic polynomial. Okay, so the zero locus of this characteristic polynomial defines a curve, and when you consider the amoeba, this is what you get. Okay, and so you should think of the amoeba as being a kind of projection of the curve in a two-dimensional space. And so the gray part is the projection, the actual projection, and the white is empty. Okay, and so now I will tell you about results on exactly the dimer model and these spectral curves. Okay, so it turns out that the spectral curves for the dimer model have remarkable properties. They're not just any curves, they are Harnack curves. And there have been quite a few results about this. So the next theorem is actually a mixture of many theorems, like summarizing all the results on this topic. So first, what Kenyon, Okunkov, and Sheffield proved, and then Kenyon, Okunkov, is that spectral curves of bipartite dimers, so bipartite dimer models, always on periodic graphs, okay, are in correspondence with Harnack curves with points on the ovals. So let me tell you what Harnack curves are. So there are different characterizations of them, but I will give you one. So here on the top, I have tried to picture a Harnack curve. I don't know if it's very convincing, But so you should think of it as being a big donut, okay, that's been projected onto the plane into the amoeba. And so such a curve is Harnack if and only if the map from the curve to the amoeba is 2 to 1. Okay, so if we go back to this amoeba, it means that if you look at the curve above, for each point here, you exactly have 2 points on your curve, exactly 2, except at singularities. Okay, so it gives you a kind of flavor of a Harnack curve being kind of quite regular. It's like a doubled amoeba that is lives in C2. There are other characterizations, but I'm not going to tell you about that. With the points on the ovals means that you have specific points around the hole here on the real locus, but I will not go into details. It's not that important for the talk. So this is a really general result that was quite remarkable, coming more from probability theory, and that really had also an impact in algebraic geometry. Then you have other types of results, that spectral curves of isoradial, so these will be specific graphs, bipart dimer models with critical weights. So I will not tell you what they are, but their specific family of weights are in correspondence with Harnack curves of genus 0. So this is a more specific result, which really identifies which dimer models correspond to Harnack curves of genus 0. So the genus of the curve is basically the number of holes. So here I have drawn a Harnack curve of genus 1. So genus 0 is essentially a sphere. Then you have, with other techniques, so more from dynamical systems, Goncharoff and Kenyon proved that spectral curves of minimal, so it's another family of graphs, bipartite dimers are in correspondence with Harnack curves with points on the oval. So this is a pendant of the first result, but with really different techniques. And they also give an explicit forward map how to go from this to from the dimers to the Harnack curve. And then there's a remarkable paper of Fock, which gives an explicit map in the other direction. But he does not restrict to Harnack curves, but to any algebraic curve. Okay, so to any algebraic curve, he assigns the spectral curve of a minimal bipartite dimer, but dimer should be put into quotes because there is no guarantee that the weights are going to be positive, so that it actually corresponds to a real dimer model. We call it dimers, but it's not dimers in the physics sense. It's a weighted graph, but the weights might be complex. But what is remarkable in this paper is that the map is explicit. Okay, and so one of our first results is that spectral curves of minimal bipartite dimer models with Fock's weights that I will tell you about. So the Fock weights, Fock's paper I talked about before, are actually in correspondence with Harnack curves of genus 1 with the point on the oval. So this result is kind of a pendant of this genus 0 result of Kenyon and Unkukov. Okay, this was in genus 0, and we have kind of a pendant result in genus 1. So we exactly identify which dimer models correspond to Harnack curves of genus 1. Okay, so now to tell you, I will tell you more specifically what are minimal graphs and then Fock's weights. Okay, so my point now is to go more into detail into this result and what goes around it. And so I will now have to tell you what are minimal graphs and also what are Fock's weights, which is a specific family of weight function. So first, minimal graphs. So there will be quite a few pictures to try to convince you of what a minimal graph is, bipartite graph. Okay, so to define minimal graphs, I have to introduce a few tools that are now, I think, quite classical in graph theory, which is the quad graph and train tracks. So it will all be with pictures. So you consider an infinite planar embedded graph G. So of course I have not drawn it as infinite, but you should think of it as being infinite. And also you consider the embedded dual graph. So for the dual, for those of you who don't know, you put a vertex for every face. So with black and white, you have, here is our graph, okay? So we will put a vertex for every face. And then we join two vertices if the corresponding faces in G are adjacent. Okay, so you can do this, and you also consider an embedded dual graph, which we'll call G star. And once you have G and G star, you can define the quad graph. So the quad graph, there are quite a lot of things on this picture, so I will try to make you understand. The quad graph is in green. So how do you build the quad graph? You take, for example, a dual vertex, and you join it to all the vertices on the boundary of the face it corresponds to. Okay, so you add quite a few edges, and you do this for every dual vertex. And actually, it's invariant through duality. You can do it also for all primal vertices. It will give you the same thing. And so now, since we have quite a lot of information on this graph, I will just remove G and G star. This is only the quad graph. And one thing that you can check quite easily if you're just sitting down for 2 minutes is that the quad graph is called like this because all faces will have degree 4. Okay, so it's a graph with faces of degree 4. And actually, something that is kind of remarkable, if you're given the quad graph, you can reconstruct G and G star. That you cannot know who is G and G star, but you can reconstruct both graphs. So you're not losing any information by considering the quad graph. And so once you have the quad graph, you can introduce train tracks. So train tracks are also known as rapidity lines in physics or de Bruijn lines. Okay, I don't know where I'm not sure of the origin of train tracks, but it should make you think of a train. So you have tracks, which are the quadrangles. And so with a line, you enter a quadrangle and you exit through the opposite edge. Okay, since you have quadrangles, this makes sense. So you always exit through opposite edges. Okay, so I'm following one train track. And so you can draw train tracks. And from the train tracks, you can also actually reconstruct the quad graph and then G and G star. So you can see a graph as a set of train tracks. Okay, so here in the picture, I've removed all information except the train tracks. Okay, and they encode important geometric information about your graph, as we will see. But first, so in the first slide, on the Harnack curves, I was speaking sometimes about isoradial graphs. So now I can tell you what an isoradial graph is. So an isoradial embedding of an infinite planar graph G is an embedding, so a way of drawing your graph into the plane, such that all of its faces are inscribed in a circle of radius 1. Few pictures, okay? So you want to inscribe all faces in a circle, and moreover, you want all circles to be of the same radius, so you can take it to be 1. And also, you want that the center of the circles are in the interior of the faces. So isoradial graphs have been introduced for many different purposes by Duffin for complex analysis on graphs, by Mercat, and by Kenyon introduced really pinpoint the term isoradial. And this is equivalent, you can convince yourself that it's equivalent to the fact that you can embed the quad graph so that all of its faces are rhombi. So I will show you a picture. Okay, so it's equivalent to having an embedding of this quad graph. You can ask this question quite generally. You're given a quad graph, can I draw it so that all of the quads are lozenges, rhombi? And so this is the same as asking to have an isoradial embedding. And so a very nice result of Kenyon and Schlenker in 2004 is that an infinite planar graph has such an isoradial embedding if and only if two conditions hold. So the first condition is that you should not have a train track which self-intersects. So this is forbidden. And you should not have train tracks, distinct train tracks, which intersect more than once. Okay, So these are the only two forbidden things. If this doesn't happen, then you will have an isoradial embedding. Okay, so now I will show you first a few pictures. These are simulations done by Cédric. So here you have a graph. You see where every face is inscribed in a circle of the same radius. So this is an isoradial embedding of a graph. Here is the graph and its dual. And here is the underlying quad graph. So with the specific embedding where all quadrangles are rhombi, okay, corresponding to the other graph. Okay, now from isoradial graphs, we will go a little bit further and go to minimal graphs. And so this definition holds for graphs that are bipartite. So in this case, when the graph is bipartite, you can add an additional structure. It's an orientation on the train tracks. So an orientation just means you're putting a direction on your train track. And so when your graph is bipartite, you can consistently arrange your train tracks in such a way that you will always have white vertices on your left and black on your right. Okay, you shouldn't look at the diamond vertices because they're the ones of the dual graph. Okay, so you look at the vertices of the original one, and you can see that you will always have white vertex on the left and black on the right. So this gives you an oriented set of train tracks. Okay, and so a graph is said to be minimal, a bipartite graph is said to be minimal if you don't have self-intersections of train tracks, as in the case of isoradial graphs, and you have more freedom. The only thing that you don't want is that train tracks, two distinct train tracks, intersect more than once in the same direction. You see here on the right, you have additional arrows. So they are allowed to cross more than once, but then they have to be in opposite directions. Okay, so it's restricted to bipartite graphs, but it's slightly more general than isoradial graphs. So they have been introduced. I guess the term minimal comes from Thurston in a paper of 2004, and then they've been studied in a different community by Gulota, Ishii, and Ueda, and also by Goncharov and Kenyon in a paper of 2013. Okay, and so we're also wondering about, how can you draw these graphs in the plane? How can you embed them? Do you have the notion of isoradial embedding? And so you have to extend this notion slightly as well. So minimal immersion of an infinite planar graph is an immersion of the quad graph such that you have rhombi, as in the isoradial case, but now you also allow rhombi to be reversed. Okay, so the embedding of your graph will not necessarily be planar. You allow edges to self-intersect. This is why we call it an immersion and not an embedding. Okay, it will not be a picture of in the plane of your graph such that edges don't self-intersect. So you allow this more freedom. And then you also ask to be consistent in some way that the immersion is flat, meaning that when you sum the rhombus angles around every vertex, then you will get 2 pi. Okay, so you're locally flat at every vertex. So this is the extension of the definition of isoradial embedding. And so maybe let's not go into too much details into this statement. But you can really characterize what this means, these two conditions. You can write them differently. And so what we proved with Cédric Boutillier and David Cimasoni is that an infinite planar bipartite graph has a minimal immersion if and only if it is minimal. Okay, so this is the right framework to extend isoradial embeddings when you consider minimal graphs. And so we will use these embeddings in our construction. Geometric properties of these embeddings. Okay, so maybe let me go back to tell you where we are now, because I said I was going to speak about 2 things. So spectral curves of minimal bipartite Darboux models with Fock weights. So now I've defined you what are minimal bipartite graphs, basically, okay? And now I will tell you what Fock's weights are to define the dimer models. So sorry, I have to go back, forward. Okay, so the dimer version of Fock's weights. So you need a few tools to define these weights. So the first tool is Jacobi's first theta function. So probably for many of you physicists, and it's a classical object. Maybe for some of you it's not so much. It's a function which has a parameter q, which is e to the I pi tau, and there is naturally an underlying lattice lambda of q, which is pi z plus pi tau z. Okay, so it's a two-dimensional lattice, and you can also naturally assign a torus, which is c quotiented by this lattice. So this defines the torus associated to the theta function. So I have not written it, but it also depends on q, and it's defined as follows. And why are these important? Because they are the building blocks of lambda periodic meromorphic functions on the torus. Okay, if you want to construct meromorphic functions on the torus, these are the basic building blocks. So they're kind of fundamental functions. So a theta function itself is not periodic. It's periodic in the horizontal direction, but it has some non-trivial period in the vertical direction. Okay, but when you combine them appropriately, then you can construct all meromorphic functions on this torus. And also another point is that it's a kind of generalization to the sine function. Okay, as q goes to 0, which is the time where you enter the trigonometric world, then you essentially have sine up to renormalization. So we need this theta function. Then the other tool is what I have introduced. It's a minimally immersed bipartite minimal graph. Okay, and so once you have this immersion, then each train track is assigned a direction e to the I2 alpha t. Okay, because you have, so maybe it's not so easy if I go back, but I think it's important that I should. When you have train tracks, if you can follow my mouse, you see you have a parallel direction that is shared by the train track. And since you have run by, all these edges have the same length, say 1. So this defines a complex vector. Okay, so to each train track, you can assign a complex vector corresponding to the parallel direction. And each edge is actually, you will see in the next slide, I think, is assigned a rhombus, so it will naturally have two parallel directions and a half angle beta minus alpha. So this information really comes from the immersion of the graph. You really use how you draw your graph in the plane. Okay, and then yeah.
I have a very naive question on the previous slide on the Jacobi theta function.
Yes.
There is nothing with the z. There is no power of n or something like that. Or the z is inside the sinus. Because that sounds like z times the constant.
Ah, yeah. No, because it's you have brackets. It's 2n plus 1z. I forgot some brackets.
Okay. Thank you.
Okay.
Very far.
Yes, right. Thank you. Thank you. Okay, and then you have the discrete Abel map. So maybe if you want just to drop for 1 minute, it's okay. It's a bit technical. Then you can just know that it's a function that is well defined. So it's defined on faces, on vertices of the quad graph, and basically you fix a base vertex where you set the discrete Abel map to be 0, and then you increase or you decrease by the angle of the train track you're crossing, and the fact that you increase or decrease depends on whether your vertex is white or black or of this kind. Okay, so you see here we're crossing alpha, so we're doing minus alpha. Here we're crossing beta. This has angle beta, and so we're adding beta, and it's a consistent mapping. And then you're also giving a point on the top. You see, this is what was entering in the lattice used in the theta function. Okay, so you're choosing a specific point. So Fock also has this point. What we're doing on top is that we're specifying the position. And then you define a Fock's adjacency matrix. So this is as before an adjacency matrix, but now the weight function is really specified. It uses the theta function and the discrete Abel map, okay, for vertex WB. So you have all the notation on the top. So they're adjacent and zero otherwise. You don't have a phase. I told you had a phase, but actually it's kind of included here because the theta function is complex in general. Okay, so this is not, that's one of the questions, is that does this really define a dimer model? Okay, do you have a phase times a positive weight function? And so this is a lemma that under the above assumption, so minimal graph, that you're choosing your T well, this is actually a KASTELEYN matrix for a dimer model with positive weights. Okay, so Fock doesn't care about being a real dimer model, and so we kind of set the assumptions, the framework where you really have a dimer model. Okay, and so this is another kind of a bit of a technical part. So the idea, putting aside the formulas, is that we want to define a function g on pairs of vertices of the quad graph time an additional complex parameter taking values in C. Okay, so in the notation, you will have the two vertices where it's defined and the complex parameter. And this function is defined by induction on the edges. So when the two vertices are the same, you just take one. And then when you have two adjacent vertices, okay, you have two definitions depending on whether it's a vertex of the dual graph and a white or a vertex of the dual graph and a black. Okay, so, and then in one direction, it's in the opposite than in the other direction. And this function g on an edge is also defined with a theta function with d and with t. And so this is for adjacent vertices. And if the distance is larger than 2, then you just take the product along a path in your quad graph of these increments. And so a lemma that can be found also in Fock, phrased a bit differently, is that the function is actually well defined, meaning that it's independent of the path you're choosing to, it's independent of the path that you're choosing to compute it. And the key fact to do everything that we want is that this function is in the kernel of the KASTELEYN operator. So KT is the KASTELEYN matrix of corresponding to Fock's weights of the infinite graph. So we kind of refer it to an operator. So this means that this is just rewritten what it means to be in the kernel. And why is such a statement true? It's because of a wonderful identity which is known as Weierstrass identity. Okay, so it's an identity of the 1900s. If you write this out, then you see that it's equivalent to having this identity, and that's why it's true. Okay. And so now we have all the tools that we need. And from these tools, we will define a map psi, which goes from the torus, so the complex torus U, into C2 as follows. It has two components, Z of U and W of U. And Z, both of them are constructed from our function G. So we assume that our graph, this is in the periodic case. And so the component Z will be the function G computed between a vertex B0 and its copy in the next fundamental domain. And W will be our function G computed from a vertex B0 to its copy in the vertical domain. So it's like a base of our lattice, and it's independent of B0 because G is well defined. So this gives you a complex function from the torus to C2. And because of the fact that G is in the kernel, you have that the map psi is an explicit birational parameterization of the spectral curve. So remember the spectral curve of the dimer model, which is the determinant of the characteristic, the spectral curve, which is the zero set of the characteristic polynomial. And so this actually gives you an explicit parameterization of the curve. Okay, so remember the Harnack curve, it's amoeba. So here I've drawn log of modulus of psi, meaning I've drawn the amoeba. And so the torus with this map psi is sent to the curve. So it's another way of seeing your curve because it's a birational parameterization. So it's a smooth between the two. And so it's actually quite precise. So the top boundary goes to the inner hole. Here you have some poles, and the poles is what gives you the tentacles. So this set goes to the outer boundary of the amoeba. And here you have two copies of the interior because you have a Harnack curve. Okay, so in the amoeba, both are put on the same thing, but in the curve, you have the two copies of each point that you see on the amoeba. And also, quite remarkably, the spectral curve is independent of T. And
just 4 minutes, 3 or 4 minutes left, probably.
Sure. So maybe I will not go to the end. Okay, I will try and state this main result. Okay. So the result that we have dependent of is the result of Kenyon, Okunkov, and Sheffield, is that the dimer model, as I was saying, answering the question in the beginning, has a two-parameter family of ergodic Gibbs measure indexed by the slope, but you don't need to know what the slope is. And also that they are obtained explicitly as weak limits of Boltzmann measures with magnetic field coordinates. And then the phase diagram is explicitly given by the amoeba of the spectral curve. Okay, so here you have gaseous phase, frozen phases, and liquids. So you see the amoeba is actually the phase diagram of your model. And so what we prove is an explicit local expression of this two-parameter family of Gibbs measure in the case of genus 1 Harnack curves. So the formula is quite general for Gibbs measure in the dimer model. What is remarkable in the formula is the expression for the inverse operator. You see, it only depends on this function g and a contour of integration. And the point u0 should be understood as it's a parameter in this formula, and it encodes the point of the phase diagram where you're at. So here is half of the domain of the torus, and it's actually the phase diagram of the. It's another way of seeing the phase diagram of the dimer model. So depending on where U is in this domain, you will have different types of contours of integration and different phases. Okay, so you should think of this domain as being the phase diagram. So let me maybe emphasize that this formula is not what you have in the result of Kenyon, Okunkov, and Sheffield. They use general theory of Fourier transformations, and you have a matrix which depends on the whole graph. Here you have this function where between B and W, you just use this function G, which you can compute inductively along the edges of a path. You don't need the information of the whole graph. So this is quite a remarkable property. Okay, I will not tell you about the proof, but maybe just to sum up, once you have such a local formula for Gibbs measure, they are very suitable to do asymptotic expansions, and you also can do compute local expression for edge probabilities. You can really explicitly, doing just residue computations, you can compute explicitly edge probabilities. I have not written the formulas in this talk, but they're just involving theta functions. And so to connect to previous work, so this is dependent of the genus 0 case of Kenyon. And before in the literature, we had handled once with Cédric and Kylian, and I did in one paper, 2 specific cases of those bipartite dimer models in genus 1. And now we have done the general case. And so what we plan to do now is to go to highest genus. So a lot of information is given in Fock's paper. He has the candidate. We have to handle positivity, and we have to learn more algebraic geometry and Riemannian geometry to understand, how do the theta functions work in higher genus. So there's some more work, but I think that a lot of the work has already been done in the genus 1 case. So this is our plan, and the Weierstrass identity is then replaced by phase 3-second identity. Okay, so I thank you for your attention.
All right, let's thank you. Are there any questions? Dominique?
Yes, I have two quick questions. The first is very naive. Does it make sense to go to more than 2 colors, 2 vertex colors? And the second one is about spectral curves. So it reminds topological recursion. Does it have a meaning there?
Okay, so the first question, so it's about bipartite. Can we go away from bipartite? That's the question, right? So that's a,
yes.
It's a real, no, I think, okay, the one fundamental thing which I have not spoken about is that in the bipartite case, you have a natural height function for the model. And because of this height function, this is where you have this phase diagram coming from. So the phase diagram is essentially indexed by the horizontal and vertical slope of your model. When your graph is not bipartite, you don't have a height function, you know that you have examples, so you don't know about the phase diagram. So the phase diagram, it's one of the really big open questions. We don't know about the phase diagram, but we believe that they're not going to be a 2-parameter family. There's no natural 2-parameter family. And also, we don't know that the dimer model will be, the curves will be Harnack. We have examples where this is not the case. So I think it's an interesting question, try and characterize spectral curves of non-bipartite dimer model, but it's difficult. And it's not Harnack, and yeah. So I think going to 3 will just, yeah, no, it's a problem. And regarding your second question, I have heard a little bit about topological recursions, but I've never heard talks where they're related to spectral curves, so I cannot answer that question.
Okay, thank you.
It looks like Pierre.
Is there, if I could ask a question, I'm sorry, they will be naive questions because I'm not in the subject.
Sure, thank you.
So in relation to statistical mechanics, my impression is that you're looking at what one would see as a partition function. Is that correct?
Okay, so the partition function, yeah, you mean the spectral curve?
Yes, and so my question is, so from the little knowledge I have of statistical mechanics, from what you're also interested in as are correlation functions. So there's a generating partition function which generates correlation functions. Do you have this concept here or not?
Yes, so when you consider the Gibbs measure, so when you have explicit expression, maybe I will go back here. So this gives you an explicit expression for Gibbs measures, okay, a 2-parameter family of Gibbs measure. And from this, you can compute correlations easily. So this is what I was saying when you're doing asymptotics, because you can take 2 edges that are far apart, okay, and so you specify this formula for 2 edges, and you can write out the correlation. And so basically the correlations for 2 edges are given by such a term for a product of 2 such terms, 2AUB, ABW. Okay, when B and W go far apart. So that's why you're interested in doing asymptotics of these formulas, because when the vertices go far apart, then you're computing correlations basically. And that's how you deduce the phase diagram. So I didn't have time to go into all details, but the phase diagram is characterized by the rate of decay of this correlation function. This is basically known as a correlation function.
Okay, so the correlation functions for 2 edges decide of the behavior for more edges? Or?
Yes, because of this determinantal structure, essentially.
Okay, okay. Because there's a kind of Gaussian pattern in the background or something like that. It's very similar to Gaussian situation.
Yeah, so so it's you get in some phases you get Gaussian processes. In the liquid phase you get Gaussian free field in the limit, okay, but not in all phases. But it's true that there's Gaussian structure. I mean, the fact that you get Gaussian free field is kind of related to this determinant form, but it's not enough. This determinant form is not enough to have Gaussian.
Okay. If I may, I'd like to make a comment, a follow-up of this very short discussion we had with Vincent before your talk about how analysis and algebra and stochastic analysis comes in blend here in this meeting and in many current topics that are being discussed. So here we had a very nice example of how probability theory mixes with algebraic geometry, and I'd like to recall that we had other talks where that was the case with signature of rough paths interpreted in algebraic geometric terms. So we can also add to the list that Vincent was giving at the beginning, before your talk, algebraic geometry blends with probability theory. Thank you very much for your talk. It was very nice.
Thank you.